this circuit on procedure section, or you can put this circuit on circuit picture on appendix C. Both are correct, okay? Both are fine, nothing wrong. Some of you using that on the procedure section, that is actually good. Then you can explain how you done that particular step, okay? That is the best way to do. For each step, put a picture and then explain how you did that. Then that is much clear how the procedure is done. Otherwise, if you want to do procedure in very short, then it is fine. Just write it down bullet form and then put the pictures on appendix C. That also fine. Okay, question so far. All right, so technically after you measure the current, I don't need these ammeters any longer, but let it be like that. Then you can see those values too. Now let's go ahead and start our table number 2. Anybody have any question at this point? Table number 2, we are going to verify the junction rule. Verify the junction rule. Now to verify the junction rule, what we need, I in and I out, right? So we're going to verify by using two methods, right? So the methods are calculated and measured, right? We have calculated values and then we have measured current. We're going to do this by using both, okay? All right, so both method, what we need, sum of all the current in, so all the current in, and also I need sum of all the current out, and then we're going to compare those two, right? So you have to have units. Make sure some of you still have this unit issue, not putting the right unit everywhere on every table. If you make a table, every column has to have a unit. That unit should usually go very top of the column. And then table name should be on the top of the table. That also some of you not doing correctly. When it comes to table name, make sure do not put the table name into one column. That is not looks fine. So the table name should be actually look like the caption. If you want to do it right way, you have to do table. You should not do the table name here. You should do in your Word file by using the caption. But if you want to do it here, that's okay. But make sure you highlight this top line and then make the table name appear to the whole table. Some of you put in the table name into one column here. Then when you copy paste, that not looks fine. Those are formatting. You have to really practice that. Okay, if you practice it, that should be good for you. Otherwise, you are not getting enough practice about this, how to do the formatting, things like that. So this is a good time to do that practice. That will be useful anyway at some point. Okay, any question? And I need current in and out. So I'm going to change this into Times New Roman, because you can see this large I look like 1 if I use a different font. Okay, so those things are formatting. You can do that later. Then again, the percentage difference between total current in and total current out, that is in percentage. Okay, so the calculated values I don't have right here. That's I'm gonna leave it you to do it later. These two values you have to do it later by using the calculated values on previous table. Okay, so the current totally coming in is only I1. So you have to have the I1 value from the previous table. Current going out gonna be I2 plus I3. So those are you have to get from the previous table. Okay, I will let you to do that. Those numbers from here. Okay, and measured values I have, right? Measured values current coming in is I1. So that is this number right there. You put equal sign and that you will get that number here. And current going out is actually I2 plus I3. Addition of these two numbers on my previous table. So I have that number. You can see very slight difference, right? So this is just because of rounding. If you round this number, you will get 0.19. So let's calculate the percent difference, equal sign, ABS, parentheses, difference between these two. we're doing percentage different always, okay? And two parentheses here, average of these two, which mean addition of those two, divide by 2, close outer parentheses, multiply by 100, okay? Get about like 1% difference. Copy that, and then we put that equation right here. That is the equation for the percentage difference. Okay, good. So this part you have to do. I will let you to do that later. And when you copy paste the table from the Excel, do not copy paste directly this equation into your data and analysis section. That is not good. So this tells some of you doing that. So these detailed calculations should show in Appendix C. So which means copy only this table, this part only to your report, and then hold this Excel sheet, which you do very detailed, put that whole Excel sheet into your Appendix C. That is how you should do in your report. So these are not information to show on your analysis section. That is not good. Report looks ugly then. Your data table looks very bad if you put all of these equations there, okay? So the one thing you actually, what you really going through here is actually observing how to do a standard report. So that's something very important in your next step, okay? Doesn't matter which field or what you're going to do next, you have to write a report. That will be your primary job, primary goal on most of the jobs. Actually, you have to write a report about something. Doesn't matter what field or who you're going to be. So you have to write the report. It's not maybe scientific publication or anything, but some sort of report to your immediate boss, or maybe the greater boss above that, and then so on. So you have to write the report always. So this is one way to get practice. Okay. All right. Any questions so far? Everybody okay? Everybody okay with this part? Any question? All right, then let's continue. All right, so that is mostly about the junction rule analysis, right? So you have all the information. Now you know what we're looking into, what we get it, and your calculated values also should be about the same, right? You have these numbers now, measured values. Now after you do the calculation, you have to check, right? If you're not getting numbers close to this, let's say you get I1 0.195, that's okay. But if you get I1 1.50, something like that, which means completely off, even like 0.22, which is not good. You have to get very close to 0.19. If you have difference in third decimal place, that's okay. 0.192, 0.191, you are fine. But if it is anything different than that, then you're doing something wrong. You have to take a look, okay? 0.189, 0.188, that's okay. But anything more than that, something wrong. So you have to take a look. Make sense? Most of the time difference is coming from this equation. Most of the time that effect is actually due to something wrong with sign rules. Okay, that's where you have to take a look. If you have any mistake, always go back and take a look the sign rule. Okay. Yes, of course. Yeah, that's what you have to do. Correct. Yeah, write it down, the information in detail, take a picture, put it into appendix. Okay, do not worry about typing those information. That's not important. Okay, good. And always take a look this equation with the sign rules. If you had any difficulty there, I will put this parentheses here to represent correctly the sign rule. I think now you can identify properly all the sign rules and everything. Okay. If something wrong, then something definitely if something wrong in these calculated values, definitely that mistake coming from these sign rules, you have to take a look. Okay, unless if you do some mistake in your algebra, that's actually should not happen anyway. These are very simple calculations. Okay guys, so any question? Can we start table 3? Everybody okay? Good. No problem. No, you don't need to. You don't need to really do this color or anything. I just put the different color because to show you that that's the equation we're doing. Don't worry about those. Okay, just you don't need to put really the colors which I using here. Okay. The equation you don't need to leave it empty. You have to have the equation here. You have to show the equation, but the color is not important. You have to have the equation really. Okay. That's what I mean. So the color is not important, but you have to show the equation on table number 1. Okay. You have to write it down, that equation. Good. Correct. Solved values goes here. I1, I2, I3, which you solving calculated. Those are actually going here. Okay. All right. Everybody got that idea? That's important. Okay. So how to format the table number 1. Okay, guys. So let's continue then. Table number 3. So the table number 3, now let's take a look the loop rules, right? So let's take a look the loop rule values first, and then let's take a look separately by using each loop rule. Now in part C, verifying the loop rule, the table number 3, we're going to verify the loop rule by using loop number 1. So the analysis of voltage, analysis of voltage of loop 1. So that's our loop rule 1, applying the loop rule for loop number 1. So in this case, first what we're going to do, not really validating the loop rule, what we're going to do, just going to take a look the voltage values, right? Because since I know already these current values, right, you can see now I already know the current values passing through each resistor. Because of that, I can calculate the voltage, right? You know, you can calculate the voltage by using Ohm's law, right? V equal IR. So I can calculate voltage across R1, R2, and R3, and R4, and R5. And then we're going to measure those voltages by using the voltmeter, right? We'll take the voltmeter and then measure the voltage. And then we'll compare those two first. Okay, that's the plan. So let's do this calculation pass first, then we measure them. Okay, so table number 3, we are on loop number 1. Loop number 1, we have 3 resistors, right? R1, R4, and R5. So V across R1, V across R4, and large R, R4, and then V across R5. I can calculate those. So let's say this is we calculated values. That is just by using IR. Unit's gonna be volt. Okay. So this is by using IR. So you know R1 value, equal sign, value of the R1, which is 18, current passing through that 0.19, right? Voltage across R1 we expecting, current passing through is 0.19 times value of R1 is 18 ohms. So that's the voltage we're going to expect. Then we will measure that voltage here. Let's say that is we measured. Okay, that is we measured. Unit is volt again. And then we're going to compare those two values here. That's a percentage different. Okay. So that is not still the loop rule analysis. This is just a voltage analysis by measuring directly and then calculate the same values by measured current. Okay, that's the plan. So use here, when we calculated, use the measured current values. Okay, these values. All right, so let's do the same thing for R4, equal sign. Value of R4, 28 ohms. Current passing through R4 is the same as current passing through R1. Okay, it's the same segment. You can see this segment right here is the same. If you want to measure that, you can always do that too, right? This is the R4. If you want to measure it, open this part right here and then bring a new ammeter. Since this is a virtual, you can bring any number of ammeters, right? So bring a new ammeter and then measure that. You can see right here, it's the same number, right? Because from here all the way to here, it's the same segment. As far as I have the same line segment, there's no any connection between them. There's no new T-type connection. Then it should be the same current. So it's 0.19. 0.19 times value of R4, which is 28 ohms. So that's the voltage we expecting there. And then R5. R5 current passing through there is 0.018, very small current, 0.018 times R5 is 12. So that's about 0.216. Okay, makes sense, everybody? Okay, since now you can see all of these measured values, I can measure all the resistance values down to 3 significant figures, and all the current values we measured up to 4 significant figures. All the calculated voltage values we can use about 3 significant figures. That's fine, I think. And then let's measure this. Now, when you measure in the voltage, you have to be careful, right? Because now when you measure in the voltage, this probe has to go relative to the battery polarities. That means, since you can see battery positive sign here, which means your positive sign relative to battery should be front of right here. And then your negative probe relative to the negative side of the battery should go here. Then you will get this negative sign. Okay, that's okay. You leave it like that because that negative sign is so important when you go into next step, not on this table, but put that number with the negative sign, because that negative sign important for our next step. Next step mean later in this table we're going to check the loop rule. When you check in the loop rule, voltage across each resistance should be negative if the current direction is same, right? You can see that correctly now you measuring, right? Put that negative sign here. But this table, that is not actually important. We are looking into just the numbers, minus sign. I'm getting 3.44. You can see it's slightly different, right? Your measured values and the calculated value. Reason is actually rounding problem happened there. So that's a problem, because it all automatically rounded into 9. Because of that, I get really little bit of percentage error. Now, one important thing here, I will write it down below here. This negative sign, I'll write it down here. Negative sign in we measured is not considered for PD cal. Okay, when you do the PD cal, do not consider that. This is important. This is important for table, I think, let's see, table number 6, I think, table number 5. When you do table number 5, that sign is important. Table 5, when you do loop rule analysis. Okay, so that is why that negative sign is important. Otherwise, right here, what we comparing just the numbers, okay? That negative sign is not important at all. So let us do maybe one column here. Might be useful, I think. Let us add another column here to represent that sign. Insert another column. Okay, so in this column, just put the V measured sign only, okay? Whether it is negative or positive. If it is negative, just put the negative sign there. and then put the number only here. Good. That way, actually, when you do the percentage different, you don't need to worry about that sign at all. Make sense? Everybody get that idea? This negative sign represent voltage drop, okay? So that is important when you do the calculation later on table number 5. I wrote it down, those information here. Okay, now we'll do the percentage different. When you do percentage different between calculated and measured, that negative sign is not important. We just need the number, okay? ABS, different between these two. Divide by average between these two. Divide by average between those two. Parentheses 100. Okay, very small percentage difference. That difference only because of actual rounding. Okay, otherwise, technically in the simulations, we should not get any percentage difference at all because it very perfect result. Only percentage difference we getting purposely because of rounding. Okay. All right, then let's measure the voltage values. Now, when you're measuring voltage values to get this sign correctly, you have to bring this probe accordingly, okay? Which means now you can see this sign is relative to this negative sign of the battery, okay? That should go behind the positive. When you go here, that is next voltage. Positive should be first, negative should come behind, then only you will see that negative sign on your voltage measurement. This is negative 0.22. That negative sign is actually not really important for this table. Sign must be negative, that is R5. Number is 0.22 and sign is negative. Okay, good. Any questions so far? And let's do the same measurement across R number 4. Make sure that probe has to be on properly adjusted, okay? Otherwise, you will not see the right sign. This is negative 5.35. I put just number there and the negative here because this negative sign is important when you do this calculation later on table number 5, okay? And let me copy paste this ABS values here, percentage different calculated values. Okay. All of these information, do not put this information on your with your table on section data and analysis section, okay? This information, extra information, anything you write it down about the table or calculation or equation, all of this information should go into appendix number C, okay? All right, good. Now to do the percentage different, you can click and drag this. That will do automatically the calculation. All right, so we done table number 3. Good, any question? Everyone okay? The sign is so important, right? So now to check immediately whether we get in the right way or not, you can do one quick check here, right? So you know the voltage supply for the loop number 1. Let's write it down, that extra information here. E for loop number 1. Loop 1 is actually 9 volt, right? That you know, 9 volt. Now, which mean if I add these measured values, that mean all the voltage drop, those are negative sign, right? So I should get negative 9, right? That's the idea. Let's do that. Let's add all of these numbers to check whether we're getting it correctly. Let's do sum of all the IR. We drop across IR. That means equal sign, minus sign, this number, minus sign, next number, minus sign, the other number. So adding all of those, I get exactly 9 volt. Okay, you can see very slight difference. This 9.01, that because of only rounding error. So this should be on unit of volt. Okay. Good, everybody good with that? Okay. So let's revoke this. These are extra information. You don't need this on your table right here, but you need them extra information later in the table number 5. So this is actually loop rule. So that's the idea. This is voltage add into the system. This is voltage drop across I and R. Okay, good. Any question? So that is why that negative sign is important. Okay. Good. Let's continue. You don't need this extra information here. Okay. You just need the table and put all the extra information on appendix C. Good. Everyone okay? Any question? Let us do the table 4 then. Table 4, we're going to do the same thing, analysis of voltage of loop 2. Voltage on loop 2. Everyone okay? Any question? Any question? No? Good. All right, then let's continue to loop number 2, table number 4. All right, so now we are on this loop right here. Loop number 2, current passing through loop number 2 is I 0.17, this segment, and then in middle segment 0.018. Okay, so let's build that table here. It's the same table actually, right? So the VCal, we measure, all of those information should be there. So I can actually copy paste this directly into here. It's going to be about the same table, but these are different now. It's not R1, instead it's going to be R2 and R3 and R5. These values I have to measure. Let's delete that. VCal, and then we measure all of these. I have to do it again. Okay. Also delete that. Okay, let's delete this negative sign also. All right, let's calculate first. Voltage across R2. Resistor R2 is 14, current passing through R2. If you want to check that again, you can break here and then bring a new ammeter and then connect here to make sure that's the same current. You can see now it's the same current on this segment, right? So that's the idea, okay? So let's calculate that equal sign. Current passing through R2 is 0.17 times resistor is 14 ohms, and equal sign current passing through R3 is 0.17. Resistor R3 is 22, and voltage across R5. Now this is important when you do this circuit, this loop number 2, you moving from this top edge right here, that is G. Let me show you on our circuit diagram here. That is G. When you do loop number 2, you can see loop direction is G to C. Okay. If you go G to C, that is opposite to current direction I number 3. Because of that, that voltage must be positive. Okay. So those are important. These voltage values negative. This voltage is actually positive. Okay, I would suggest put that sign accordingly. That will be useful when you do actually next calculation later on table number 5. That must be a negative sign. This must be also negative. This must be also negative on previous. Okay, which means I can actually keep those negative sign all of these measured values directly. Okay, let me do one quick adjustment here. That should be ABS absolute value only. All of this. Okay. Make sure your percentage error cannot be negative at all. Okay. Any percentage error you calculating, percentage error or difference, both should be only absolute. Okay, so let's continue. Now these two are positive, we know, but this one is negative, okay, because of that equal sign minus current passing through mid section right here, which is 0.18, 0.018, 0.018 times resistor value there is 12 ohms. That's the only negative sign there. Okay, loop number 2. Sorry, that is only positive value there on loop number 2, and these two should be negative. Anybody have any question? I did this adjustment because actually later that is important, because you know when you go in, let me explain that again. When you're going through the circuit, if you pass in through the resistor, what you're checking is the current direction, conventional current direction. This is red arrow, and your loop direction, right? If your loop direction and the current direction same, that voltage must be negative. Let me do this for loop number 2. Across R2, current and loop direction same, negative. Across R3, current and loop direction same, negative. But across R5, loop number 2, loop direction and current direction opposite. Because of that, this value must be positive. Got it? Everybody okay with that? Everybody okay with that? Have any question? Okay, so let's measure this then with the sign, okay, including the sign. All right, so you know how to measure now. When you're measuring, make sure one thing I mentioned earlier, this is actually, if you're doing this in class, that is one very important concept. You have to bring this probe relative to the battery, okay? This is battery negative, so this should be negative. So the battery positive should be on the front, right here. Why not showing me anything? Let me check it here. Now voltmeter seems to be not giving us any numbers. Why is that? All right, now it's fine. Oh, good, yeah. So I was measuring across the ammeter. You can't measure anything across the ammeter. That not make sense, okay? So you have to measure across resistance only. So relative to negative sign of the battery, this should be here. Relative to positive sign of the battery, this should be here. Make sense? If you do that correctly, then only you will get the right sign relative to our Kirchhoff rule, okay? That's important. Negative 3.8. That is across R3 with minus sign, minus 3.8. Type here to tell that is negative sign 2. And let me measure across next resistor. When you measure in that, remember, positive sign should be front, negative probe should be behind. Okay, if you measure it correctly, now you can see it is positive 0.22. Okay, that's what I was explaining earlier, which means this one now, which is actually positive 0.22. So this one should be with the positive sign. So that's our relative sign for the Kirchhoff rule. Okay, let's measure now last one, resistor number 2. Negative 2.42, negative sign, 2.42, which is also negative. Okay, good. Any question so far? And also make sure you format this to represent at least 2 decimal places. Okay. Let's do percentage different. Again, the same thing, all of this information again is valid. Okay, whatever the information we discussed, table number 3, that negative sign is actually represent the direction of the loop, relative direction of the loop, and the current direction, conventional current direction. All of those informations are needed for table number 5 when we really doing the loop rule analysis. Okay, that's the plan. Okay, question. No questions? Okay, let's continue then. Let's calculate the percentage difference. Equal sign. ABAs. Different between these two. One minus the other. Divide by average between these two. One plus the other. Divide by 2. Close parentheses. Multiply by 100. That's extra parentheses here. Yes, one parenthesis missing. Let me take a look at ABA is different between those two. Divide by addition between these two, and there should be one more parenthesis here. Okay, good. And then you click and drag. Then it will do the calculation automatically for you. Now, amount of significant figures, I can't actually have this many of significant figures on my calculated values. That is still some of you doing that mistake. After you do the calculation, I will change all of these calculated values to show about 3 significant figures. Okay. So which mean maybe in decimal places, 2. If you do that, then all the formatting going to be looks nice. There's no huge point reduction for your significant figure problem, but that something is important to take a look really, that is actually useful as you go into your next step. Most of the engineering problem, when you're measuring something, reporting those values, those are extremely important, those numbers. Later when you work in the industry, you will realize that when you measure something, when you report it, it's extremely important to report the accuracy and everything. All those informations are very useful because you report that to another person, right? When that person read your report, that person should identify how much the accuracy you're reporting in your measured values. Then in your calculated values, do you have the same accuracy reported correctly, and then so on. That's something useful to practice anyway. Okay, guys, any questions so far? Good, no problem. This measured value, this voltage, I keep that this 2.216 because you can see if I rounded that to 0.22, then you will see automatically you will get 0% error, right? So the part of this labs in physics lab, what we really like to see is how much error is happening any of the measurements when we done. That's something which is difficult to do with the virtual setup. You will not get the percentage errors or anything because it's perfect result. But if you do this in class, you will get sometime 10-20% error. If you do very careful job, you can minimize that to maybe 5 or less percentage. That is a good accepted value for in-class experiment. Otherwise, most of the time we're getting higher percentage error. A simple mistake, even these probes, this connection, wires, sometime in class we have actually considerable resistance effect depending on the how we use it, and then the cables and then everything. He's adding a little bit of percentage error. Okay. Any questions so far? Everybody okay up to table number 4? Good. Any question? Table 1, table 2, table 3, table 4. Everybody okay? All right. Then let's take a look. Table number 4. Now in table number 4, what we're going to take a look, the outer loop. We did not discuss that much. Table number, I'm going to create another table here. That is not on your circuit, but let's create that one. Let's create another table called table 5. This is actually we're going to do the same thing, analysis of voltage in outer loops. Okay, outer loop is actually, let me show you that. Generally that is not important, but since we do this experiment virtually, that is actually useful to check. Outer loop is this one. Let me go back to here. Now, if you take a look your circuit, the outer loop is starting from A, B, C, D, F, G back to A. You can see that outer large loop, right? So that is another loop, right? So which means technically when you apply the loop rule here, you can apply loop rule for inner loop. This is small one, left-hand side, a small loop, right-hand side, and the outer loop. So if you do outer loop rule, then you're going to start from A to B, B to C, C to D, D to F, F to G, G to A, right? Then I can check the loop rule again by using outer loop. That's a plan, right? So which means if you go this outer loop, you have two voltage supply, E1 and E2, and then you have four resistors, right? Across four resistors, R1, R2, R3, R4, you will get the voltage drop. Let's check that too. That will be useful. It's the same exact thing, okay? There's no anything big different, same exact thing. You can copy paste this table and then you can easily modify that. So now we are on outer loop. Outer loop means let us name that too. Outer loop is starting from A, B, C, D, F, G back to A, okay? That's the outer loop. Make sense? Everyone okay with that? Let's delete these values. Now I need voltage across R1, voltage across R2, voltage across R3, and then voltage across R4. Good, everybody okay? No question? Okay, let us do the voltage calculated values. Now you know R1, which is 18, current passing through that 0.19. And that must be a negative number because you can see when you're moving from A to B to B to C, loop direction is B to C, current direction is the same. This should be a negative sign, okay? Negative sign. Current passing through is 0.19. 0.19. Resistance of that is 18, okay? Good. And then similar R2, this one right here. Current passing through 0.17, resistance there is 14. R3 right here on the top, current passing through there 0.17 times resistance there 22. Current passing through R4 equal sign is still negative because the loop and current direction is same. Current passing through resistor number 4, 0.19, and then resistance is 28. Now you can see, to do the quick check, if you add all of these voltage values, right, that is voltage drop, right? Let's add those things. So this is actually sum of all the INRs, right? So let's add all of those together. You can add all of those by using the command called sum. parentheses, add all of these together. Then you're getting voltage 14.86, right? Then let's add all the batteries together, sum of all the E's. So sum of all the E's on your outer loop, battery number 1, 9 volt. If you go across the other side, battery number 2 is still the positive battery. It should be a positive sign. So the 9 plus 6, you will get 15, right? So you're getting here positive 15. Now let me change both of them into two significant figures. Sorry, two decimal places to show the accuracy. So that means I have a little bit of percentage error between them. We expecting 15 voltage drop and then 15 voltage add, but you're getting slightly different when you do sum of IR. The reason is actually rounding from the current values, okay? This is sum of all the E's. Okay, good. This is extra part I just added into there because that loop also we can analyze by using there. Okay, that is not on your lab. That is not in your lab given information here, but that is something important. Okay, good equation so far. So please add that table too. Because of that, you should have 6 tables altogether on your table on your report. Okay, not 5. Everybody see that any question on there? Now we are doing the outer loop analysis. When you do the calculation, actually you can use that loop too. The problem is that I need only 3 equation. So if you try to do this loop rule only to build the 3 equation, so your answers will not be possible. The reason, you will get the same variables again like on your previous 2 equation on your last one too. Let me explain that again. So if you want to calculate current I1, I2, I3, you need 3 equations, right? So if you build 3 equation by using only loop rule, what's going to happen? Your third equation from the outer loop will be same as the addition of these two together. It's not the different equation. So that's why when you do this calculation right here, we did the inner loop 1, inner loop 2, and the junction rule because I need 3 different equations. Okay, that's why. Otherwise, you have freedom to use that outer loop in any questions as needed. Okay, everybody get that idea? Question? Any question? All right, so let's measure this one then. All right, now we're going to start again from this point, okay? So let me go back to this. We need board diagram. This diagram, now we are on outer loop. We're going to start from A, right? A to B, B to C, C to D, D to F, F to G, and then G to A, okay? We need voltage across R1, R2, R3, R4. So let's measure them again. Remember, when you measure in the voltage, you have to bring these probes relative to the battery, okay? Battery negative here, relative to that negative probe here. Battery positive here, relative to that battery positive there. Then you will see that negative sign in your voltage meter or the ammeter, which means this should be sign negative, and the voltage measured across that 3.44 negative. Everybody okay with that? Following? Those numbers earlier you measured, actually you can directly extract too, but let's measure it again. And then across here, positive probe should be there, negative probe should be here. Negative 2.42, sign negative, value negative 2.42. Okay, then next one, positive should go first, negative should come behind. Sorry, across resistor here. That is resistor number 3, sign negative, measured value minus 3.80. And the last one, positive should go first, negative should come behind. That is our number 4, Sign negative. Value measured 5.35 negative. Okay, you can see slightly different numbers on second decimal place. That reason is only because of our rounding error. Okay, otherwise should not have any errors on this measurement values. Let's do the percentage different. Equal sign, ABS, two parentheses, different between these two, divide by two parentheses, addition between these two, divide by 2, close parentheses, twice, multiply by 100, you will get the percentage different, close, click and drag, you will get the percentage different, automatically calculate for the rest. Let me copy that percentage different equation here. Okay, and then make sure do not use this extra information, these equation, things like that on your data and analysis section. But please add those information on your appendix C. Okay. Okay, guys. Everybody okay with that? Good. No problem. Everybody got it? So that's the outer loop analysis. Okay. That's the extra part that, but that will give you better idea about the. This is a simple circuit, right? Simple circuit, only two loops, but you can see how much information we can study by using that simple circuit, right? So that's the idea. Okay, so any question? And also I check extra other information right here, right? So that information, all of those information we need actually table number 6. Let's do table number 6. Now on there, we actually gonna check the loop rule. So analysis of loop rule. No, percentage different, percentage error can't be negative. That must be only a positive number, not acceptable. You have to change, you have to put ABS. That's the whole idea of doing this ABS. Okay, ABS is absolute value. So if you do it correctly, then that should come with the positive number. Okay. All right, so analysis of loop rules. Analysis of loop rule. Okay, so we're going to do that analysis for each rule, right? If you take a look at this last table, this called table number 5 on your lab manual, but since we add this extra table, that should be now table number 6. Okay, make sure you follow that. And this table, we're going to do all 3 loops. You can see we're going to analyze loop number 1, loop number 2, loop number 3. Okay. All right, so let's take a look. So we're going to do analysis on loop 1. Inner loop 1 is starting A, B, C, G back to A. Then we're going to do inner loop 2. So that is starting from D, F, G, C back to D. Then outer loop, right? So the outer loop, which is starting from A, B, C, D, F, G back to A. So that's the outer loop which we done earlier. So all of this information you already measured. Okay, you don't need to remeasure anything. Table number 6, all the information you have on earlier 3 tables. Okay, last 3 tables you have them. So table number 4, table number 3, and table number 5, you have all the information. You just need to do the calculation. Okay, that's all. So let's take a look. I first need all the voltage added into the circuit. That means technically sum of all the E's, right? Sum of all the E values we need, unit of volt, and then I need sum of all the I and R, unit volt, and we need then sum of all the V measured. Okay, sum of all the IR is actually calculated values. Then I need sum of all the V's. Sum of all the V's. These are measured values, okay? That also voltage V. And then you have to do percentage different twice for these, right? Let me expand these columns a little bit, size of the columns. Make it larger. Okay, so now when you do this percentage different, we need to do percentage different twice. One is actually sum of all the E versus IR, okay? So it says here percentage different voltage supply and then voltage drop calculated, okay? This is actually between first this column right here and sum of IR, okay? Percentage different, I will write it down parentheses here. This is between E's, that's the voltage added, versus between voltage calculated, that is IRs, okay? And then you have to do percentage different again, one more time. That percentage between voltage added, that is versus voltage drop, that is measured voltage. We say that is just the V, okay? Voltage measured, all of these percentage sign. Okay, so all of these calculation we can do by using the numbers already in on your previous table. Now, I need the loop number one information on our table number one right here, right? Loop number one. Voltage addition is only 9 volt. There's only one battery there, right? I have that information. So that means it's going to be just plus 9 volt. You can reformat this whole thing into at least two decimal places to show the accuracy. Sum of all the IR, which means your table number 3, you have those information. Table number 3, sum of all the VCal right here is actually that, right? So the VCal we done by using INR. That information you have there, you just need to add all of this information into here. So which means you can do equal sign, sum, parentheses, you go into table number 3 and then add these three values, okay? These three values together, close parentheses, hit enter button, it will automatically do the calculation for you. Now you can see these two should be one positive, one should be negative, right? Because the reason this is actually voltage adding, this is voltage drop. So you should get that negative sign. But remember, when you do percentage different, that negative sign, we don't care. Okay, that negative sign you have to get rid of when you do percentage error, percentage different calculation. Okay, sum of all the V measured, then again equal sign, sum, parentheses, that is table number 3, voltage measured, these values, these three values, close brackets, equal sign, you will get the answer. That also again negative. Reason that's voltage drop measured. That voltage drop represent that negative sign. But technically loop number 1, this analysis, I don't need that negative sign at all. Okay, I'm interested only measured values directly. Okay, good. Okay, any question? Everybody okay with that? You can see these three numbers. If you're doing it correctly, after you do this table for next two loops, these three numbers should be about the same, okay? About the same. These three represent is actually this negative sign to represent that is voltage drop because our Kirchhoff rule comes with the sign rule, okay? All right, guys, any question? So let's do the percentage different then. Absolute value, ABS, parentheses. Now I need different E's versus INR. This is C minus, when you do this INR, that should be a positive number. Okay, I just need that number. So what I'm going to do, I'm going to type that number 8.96 instead of click here. Otherwise, it's going to come with that negative sign. Okay. close parentheses, divide by double parentheses, average between them, 9 plus 8.96, close parentheses, divide by 2, close it again, multiply by 100. That's important the way I done that. The reason otherwise, if you just do it by clicking that cell, that negative sign will show up. As a result, you will get the huge problem. Okay, this is for percentage different calculation. You can see, get rid of that negative sign. I just put that number there directly. Or what you can do it this way too. You can add another negative sign here. When you do that calculation, you can do this way also if you want to. I want to get rid of that negative sign, put extra negative sign, delete this part, and then click that cell. So that will get rid of that negative problem. Okay. So this is also the same. Add extra negative sign and then click that cell. Okay, that also will get rid of that negative issue. Okay. Otherwise, you might get really large percentage error or something. If you get that, the problem is that. Okay, good. You have to take care of that negative sign when you do the percentage error. But leave it on the table because that is representing sum of all the e's should be equal to sum of all the r. So that's what it represents. Good. Any question so far? All right, then let's do other two. So let's do loop number 2. Loop number 2 results are on table number 4. So I need all the potential added into this loop. So all the potential added are actually only one battery on there, right? Loop number 2. Let us go back and take a look. Loop number 2 has only this battery, that is 6 volt, right? So which means loop number 2 added voltage is only 6 volt, 6.00. And sum of all the I and R equal sign, sum parentheses, those numbers, table number 4, we calculated. These three are sum of all the I and R's. You can see these two should be very close, okay? If you're not getting that, you're doing something wrong, okay? That's how you're going to take a look. Then I need measured values, sum, parentheses, all these details on table number 4. Measured values right here. These three are measured values. You can see that exactly the same, okay, in this case. Then percentage different. You can copy paste this actually directly there. That will do it for you automatically. Let me do this percentage different also. You can copy paste this one here to here, but you have to readjust, okay. ABS parentheses different between E and B, minus parentheses, another minus, this guy, close parentheses twice, divide by parentheses, addition between these two, plus parentheses, another negative sign, this guy, close parentheses twice, divide by 2, close parentheses again, multiply by 100. Let me copy paste that also. That is actually percentage error for the second one, okay, percentage different. Okay, question. This is percentage different on cell E. This is for cell E. This percentage different is for cell F, okay. Parentheses, cell F. Okay, question. Then to do any others, the same column, if you do the same thing, you can always click and drag or copy paste. Then you will get automatically that calculation. This is 0 because you can see this is the same number, okay. And then last one is the outer loop. Any questions so far? Everybody okay? We done all the calculation, okay. Last one, outer loop. All the information outer loop you can see on this table number 5. Voltage addition is actually sum of all the is 15. I have it there. Okay, then equal sign, sum, parentheses. We calculated these actually these 4 values, close parentheses. You can see I'm getting about very close number. Then some parentheses, voltage measured, these 4 values, close parentheses. Now we're getting very, very close values, right? So let's copy paste these two here. Then you have the percentage different values. Okay. All right, guys. So any question? So we done all the calculation and everything.